The universe began in fire and chaos, a swirling sea of raw energy where no atoms could survive. But then came the first whispers of chemistry, the moment when simple particles started dancing together to form something new. How did these earliest reactions shape the cosmos we see today? What hidden forces sparked the transformation from emptiness to everything? We're about to dive into 30 astonishing theories, from the violent collisions of newborn stars to quantum ripples that may have written the first cosmic recipes. Some of these ideas will challenge everything you thought you knew about the dawn of existence. Others might just make you gasp, so hold tight. We're rewinding 13.8 billion years to witness the universe's very first chemical secrets. Imagine the universe just moments after the Big Bang, an unimaginably hot, dense soup of energy where matter as we know it didn't even exist yet. But within that seething chaos, the first chemical reactions were already taking shape. This is primordial nucleosynthesis, the process that birthed the very first atoms in existence. As temperatures cooled from trillions of degrees, protons and neutrons finally had a chance to stick together, forming the nuclei of hydrogen and helium, the building blocks of everything to come. No stars, no planets, just these raw ingredients forged in the furnace of creation itself. Scientists calculate that in those first 20 minutes, nearly all the helium in the universe was formed, along with traces of lithium. It sounds simple, but without this crucial phase, galaxies could never have ignited, and life as we know it would be impossible. Yet here's the wild part: this theory isn't just speculation. The observed ratio of hydrogen to helium in space matches these predictions almost perfectly, making it one of the strongest pillars in modern cosmology. So when you look up at the night sky, you're seeing the direct descendants of those first primal reactions, echoes of a time when the universe was still writing its very first chemical laws. But what if those first atomic bonds weren't just shaped by temperature and density, but by something far stranger? Beneath the surface of the newborn universe, quantum fluctuations were flickering into existence, vanishing as quickly as they appeared. These microscopic ripples in space-time might seem insignificant, but they could have been the hidden architects of chemistry itself. Picture this: a fleeting quantum wobble briefly concentrates energy in one spot, just enough for particles to overcome their natural repulsion and snap together. Some scientists argue these random sparks could have jump-started the first hydrogen molecules, acting like cosmic matchsticks in the dark. Others push back: if quantum effects steered early chemistry, was it all just chance? Or did deeper laws of physics guide the chaos into order? The truth might lie in between. Recent simulations show how quantum randomness could have created patches of higher density where reactions thrived, almost like invisible currents stirring a primordial soup. Whether accident or design, one thing's certain: those ghostly quantum whispers may have set the stage for every molecule that followed, from stardust to DNA. Now let's venture into one of the most mysterious frontiers of cosmic chemistry: dark matter's possible role in the universe's first reactions. We know dark matter outnumbers normal matter 5 to 1, yet it barely interacts with anything we can see. But what if, in those earliest moments, these shadowy particles played an unseen hand in shaping chemistry itself? Some physicists speculate that certain types of dark matter could have acted like cosmic matchmakers, briefly influencing ordinary particles to bond when they otherwise wouldn't. Advanced computer models show how these phantom interactions might have created pockets where hydrogen and helium formed faster, almost as if guided by invisible scaffolding. Of course, this idea remains hotly debated. Without direct proof of dark matter's true nature, we're left with tantalizing simulations and a mountain of questions. Could the very structure of our universe owe its existence to something we still can't detect? If future experiments confirm even a fraction of this theory, it would rewrite not just chemistry's origin story, but our entire understanding of the cosmos' hidden architecture. High above the swirling chaos of the early universe, another invisible force was at work: cosmic rays, torrents of high-energy particles screaming through space at nearly the speed of light. These weren't just passive spectators in the drama of creation. They were demolition crews and architects rolled into one. When a cosmic ray smashed into one of those fragile first molecules, hydrogen, helium, or even trace lithium, it didn't just knock things loose. It shattered them into reactive shards, hungry for new bonds. Picture a glass vase exploding into sharp fragments, each one capable of piercing and clinging to whatever it touches next. That's what was happening on an atomic scale, with broken particles ricocheting through the infant cosmos, sparking chain reactions no gentle chemistry could achieve. Fast forward to today, and astrochemists are finding echoes of this violent process in places you'd least expect. Deep inside interstellar clouds where new stars are born, telescopes have spotted bizarre molecules that shouldn't exist under normal conditions until researchers realized cosmic rays are still at it, bombarding dust and gas to forge compounds nature wouldn't make otherwise. It's like discovering an ancient, unkillable wildfire still burning in hidden corners of the universe. But here's the twist: some scientists argue these high-energy reactions didn't just create chaos, they may have set the table for life itself. The same fragmentation that destroyed also built, crafting complex precursors to water, ammonia, even amino acids. So next time you hear about cosmic rays, remember, their violence might have been the crucible that forged the universe's first steps toward chemistry and us. Picture the early universe not as a placid soup of gas, but as a churning ocean of plasma, a state so energetic that atoms couldn't even hold onto their electrons. This superheated frenzy might seem like the last place for chemistry to take root, yet some researchers believe it was the perfect storm for the universe's first molecular handshakes. Unlike the orderly reactions we see in labs today, plasma phase chemistry works differently: charged particles, or ions, zipping through space, their electric charges overcoming the usual barriers to bonding. Imagine trying to shake hands with someone while both of you are covered in static electricity. Sparks fly, connections snap into place unexpectedly. This wasn't just a scaled-up version of modern chemistry either. Under those extreme conditions, particles behaved in ways that defied textbook rules, forming fleeting alliances that wouldn't survive in cooler environments. Think of it like a crowded dance floor where everyone's moving too fast to pair off normally, yet somehow brief duets keep emerging from the chaos. Modern plasma experiments here on Earth offer clues. When scientists recreate these conditions, they observe bizarre molecule-like structures forming between ions, lasting just microseconds before flying apart. If similar reactions happened in the early universe, they could have laid the groundwork for more stable bonds as things cooled down. But here's where it gets even stranger. While stars fuse atoms under immense pressure and heat, plasma phase reactions didn't need that kind of squeeze, just raw, unfiltered energy. Some models suggest these ion-driven processes might have produced early heavy elements faster than stellar fusion ever could, like a cosmic shortcut before stars even existed. Of course, not everyone's convinced without direct evidence from that era. It's still a hypothesis. Yet if future telescopes spot unusual molecular signatures in the farthest reaches of space, where ancient plasma once ruled, we might finally get proof that chemistry's wildest phase was also its most creative. Now let's turn to one of the most radical ideas about the universe's first chemical reactions: primordial black holes. These aren't the colossal voids left by dying stars. These would have been microscopic specks, smaller than an atom, born in the chaos of the Big Bang itself. Imagine them as cosmic pinpricks, each weighing as much as a mountain yet compressed into a space tinier than a single proton. Their gravity would have been intense enough to yank nearby particles into tight knots, creating extreme conditions where matter behaved in ways we can barely simulate today. Here's where things get fascinating. As these tiny black holes zipped through the early universe, they could have acted like frenzied molecular workshops, forcing hydrogen and helium atoms so close together that they overcame their natural resistance and fused. Normally, this kind of bonding would need the crushing pressures inside stars, but primordial black holes might have offered a shortcut. Some calculations even suggest they could have generated heavy elements like carbon or oxygen billions of years before the first stars lit up. It's a wild thought, black holes not as destroyers but as midwives for the building blocks of life. Yet there's a catch: no one's ever detected one of these ancient relics. The math works, but the evidence remains frustratingly elusive. That hasn't stopped theorists from dreaming up ways they might still be hiding in plain sight, maybe lurking in the cores of planets or zipping through our solar system unnoticed. If they exist, their fingerprints could be written in the odd distribution of elements across the cosmos, or even in the way galaxies clump together. Until then, primordial black holes remain one of astrophysics' boldest what-ifs, a tantalizing maybe at the edge of our understanding, whispering that the universe's first chemistry might have been forged in the darkest crucibles imaginable. At the cutting edge of theoretical physics lies an idea so elegant it could rewrite our understanding of the universe's first moments: supersymmetry. This concept suggests every known particle has a hidden twin, a heavier superpartner waiting to be discovered. But here's where it gets revolutionary. As these exotic particles decayed in the early universe, they might have unleashed cascades of energy that kick-started the first chemical reactions. Imagine a cosmic domino effect, each heavy supersymmetric particle splitting into lighter ones, releasing sparks of radiation that helped hydrogen and helium atoms find each other in the darkness. String theory paints an even wilder picture. If these superpartners existed, their interactions could have sculpted the early cosmos like invisible hands, guiding matter into the precise arrangements needed for chemistry to flourish. Some models suggest their decays left behind not just raw elements but complex molecular precursors like cosmic breadcrumbs leading toward life itself. Yet despite decades of searching, particle colliders haven't spotted these elusive twins. Why? Their masses might be just beyond our current reach, hiding in energy ranges today's machines can't probe. Or perhaps they're stealthier than predicted, leaving subtler traces in the quantum foam. The hunt isn't over. Upgraded colliders and deep space observatories could still uncover clues, anomalies in cosmic ray data, or unexpected particle behaviors that hint at supersymmetry's fingerprints. Until then, this theory remains a breathtaking what-if, reminding us that the universe's first chemistry might have been shaped by particles we've yet to meet. Now let's consider a time when the universe wasn't just expanding, it was exploding outward at speeds beyond comprehension. This was the inflationary epoch, a blink of cosmic time when space itself stretched faster than light, doubling in size again and again in fractions of a second. But here's the twist: this hyper-expansion might have left frozen fingerprints in the very first chemical reactions. Think about a pot of boiling water suddenly flash frozen. The bubbles trapped mid-pop, the steam crystallized into jagged sculptures. Inflation could have done something similar to the universe's earliest chemistry. As particles raced to bond, the violent stretching of space may have yanked them apart mid-reaction, locking incomplete molecular structures into place like cosmic fossils. Some researchers believe these half-finished reactions left subtle scars in the cosmic microwave background, the afterglow of the Big Bang itself. Tiny temperature fluctuations in this ancient light might be echoes of chemical processes abruptly cut short. Not all scientists agree, though. Critics argue inflation happened too early for any meaningful chemistry, just energy too hot for atoms, let alone molecules. But supporters counter with simulations showing how quantum ripples during inflation could have seeded later chemical irregularities, like invisible blueprints waiting to unfold. Whether inflation actively shaped chemistry or just set the table for it, one thing's certain: those first instants of cosmic stretching might hold secrets we're only beginning to decode. And if future telescopes spot the right anomalies in that primordial glow, we could be looking at snapshots of the universe's first attempts at chemistry frozen in time. Among the universe's most elusive particles, neutrinos drift through space like cosmic phantoms. Trillions pass through your body every second without a trace. Yet in the earliest moments of creation, these ghostly particles might have played a surprising role in forging the first chemical bonds. Here's the twist: while neutrinos barely interact with matter today, the infant universe was so densely packed that even they couldn't slip through untouched. In those extreme conditions, a fleeting collision with a neutrino could have been the nudge that sparked atomic handshakes. Picture this: a sea of hydrogen nuclei and free electrons, so crowded that particles barely move without bumping into something. Enter a high-energy neutrino zipping through the chaos. Most times it would pass right through, but in rare moments, it might graze an electron, transferring just enough energy to send it hurtling toward a waiting proton. That tiny burst could have been the push needed to overcome their natural repulsion, allowing them to snap together into stable hydrogen atoms. What makes this idea so compelling isn't just the math, it's the echoes we might still detect. If neutrinos helped catalyze early chemistry, their fingerprints could linger in the uneven distribution of matter across the cosmos. Telescopes mapping the universe's large-scale structure have spotted curious overdensities pockets where galaxies cluster more tightly than expected. Some theorists argue these could be relics of regions where neutrino interactions were more frequent, leaving behind cosmic hotspots where chemistry got a head start. Of course, not everyone's convinced. Skeptics point out that even in the early universe, neutrinos' interactions would have been vanishingly rare, like trying to light a fire with sparks that almost never land. But supporters counter with simulations showing how, over millions of years, those rare events could have added up, especially where matter was already densely packed. It's a reminder that in the vast tapestry of cosmic history, even the faintest threads might have pulled their weight. So next time you hear about neutrinos, remember, these shadowy particles might have been silent partners in the universe's very first atomic dance. Early in the universe's story, there should have been a perfect balance, equal parts matter and antimatter, destined to annihilate each other in bursts of pure energy. Yet here we are, in a cosmos filled with galaxies, stars, and planets made of matter. How did this imbalance happen? The answer might lie in baryogenesis, the process that tipped the scales and possibly jump-started chemistry itself. Picture a cosmic battlefield where particles and antiparticles collide and vanish except for one crucial detail. For every billion annihilations, a handful of matter particles survived. That tiny excess became everything we see today. But here's the twist: this imbalance didn't just leave behind raw ingredients, it created the perfect conditions for chemistry to thrive. Without it, the universe would have been an empty bath of radiation with no stable atoms left to bond. This isn't just speculation. Soviet physicist Andrei Sakharov outlined 3 essential conditions for baryogenesis. First, the universe had to be out of thermal equilibrium, a state where matter could escape annihilation. Second, there needed to be processes that violated both charge and parity symmetry, allowing matter to dominate. And third, these imbalances had to persist long enough for matter to stabilize. Now tie that to chemistry's origins. Those surviving baryons, protons and neutrons became the foundation for hydrogen and helium nuclei. If antimatter had won, those first bonds could never have formed. Even more fascinating, some theories suggest the same exotic particles responsible for baryogenesis, like hypothetical X bosons, might have also triggered cascading reactions, turning lone protons into the first atomic seeds. The echoes of this imbalance are everywhere. Modern particle colliders recreate fragments of these extreme conditions, hunting for the minute differences between matter and antimatter that could explain why we exist at all. If they succeed, it won't just solve an ancient cosmic mystery. It'll reveal how the universe's very first chemistry emerged from what should have been total annihilation. Before atoms, before protons and neutrons, the universe was a seething ocean of something stranger: quarks and gluons, the most fundamental particles imaginable, moving freely in a state so extreme it defies our everyday physics. This was the quark-gluon plasma era, a fleeting chapter when temperatures soared so high that even atomic nuclei couldn't hold together. Yet in that primordial soup, the seeds of chemistry might have already been stirring. Scientists recreate these conditions today using massive particle colliders, slamming heavy ions together at nearly light speed to produce microscopic bursts of quark-gluon plasma. What they've found is astonishing. Even in these extreme states, brief, molecule-like structures seem to flicker into existence, lasting mere trillionths of a second before dissolving back into chaos. Think of it like waves forming in a stormy sea, momentary patterns emerging from the fury before vanishing again. Some theorists believe these fleeting proto-molecules could have been chemistry's earliest precursors, forged not by gentle bonds but by sheer brute force. The quark-gluon plasma wasn't just a featureless soup, it had texture, regions where quarks clustered in ways that mimicked molecular behavior without stable atoms to anchor them. If so, this might mean the universe was experimenting with chemistry long before the first true molecules ever formed. Not everyone's convinced, though. Critics argue these structures are too unstable to have had any lasting influence, but supporters counter with simulations showing how quark-level interactions could have left subtle imprints on matter's later organization, like invisible guidelines for how particles should eventually arrange themselves. Whether these fleeting bonds mattered or not, one thing's clear: the universe's first chemical experiments might have been wilder, messier, and more inventive than anything we've ever imagined. And deep inside today's colliders, we might be catching glimpses of that untamed era, replaying the universe's earliest attempts at order in a storm of pure energy. Now imagine the early universe threaded with invisible cracks, cosmic strings thinner than an atom yet stretching across light years, or domain walls like vast, shimmering sheets dividing space itself. These bizarre structures, called topological defects, might have been the universe's first chemistry labs. According to some theories, these defects weren't just cosmic oddities. They could have acted like gravitational funnels, pulling in particles and concentrating them into dense hotspots where reactions ignited far faster than elsewhere in the universe. Picture it like raindrops gathering along a spider's web, except here, the web is made of pure spacetime curvature, and the droplets are clouds of hydrogen and helium atoms. The extreme conditions near these defects could have crushed particles together with enough force to overcome their natural resistance, jump-starting molecular bonds that otherwise might have taken eons to form. Some simulations even suggest these regions may have cooked up trace amounts of heavier elements long before stars could forge them, like cosmic shortcuts hidden in the fabric of reality. So why haven't we spotted these relics? Their fingerprints could be hiding in plain sight. If cosmic strings or domain walls existed, they'd leave subtle ripples in the cosmic microwave background, tiny temperature variations that telescopes are now scanning for. Others think their legacy might be etched into the distribution of galaxies, with clusters forming along the ghostly scaffolding these defects once provided. Not all physicists are convinced, though. Critics argue that most defect models predict effects too faint to detect, or that inflation should have erased them entirely. Yet the hunt continues, because if even one of these cosmic scars is found, it would mean the first chemical reactions didn't just happen randomly. They were guided by the hidden architecture of spacetime itself, written into the universe's blueprint from the very first moments. Let's venture into one of the most mind-bending ideas in modern physics, the holographic principle, and how it might rewrite the origin of chemistry itself. At its core, this theory suggests our three-dimensional universe, with all its complexity, could actually be a projection of information encoded on a distant two-dimensional surface. If that sounds like science fiction, hold on, because if true, it means the first chemical reactions weren't just happening in space, they were being computed on the cosmic equivalent of a flat screen. Think of it like a movie projected onto a theater wall. The images appear three-dimensional, but every detail originates from data on a flat film reel. Now imagine that reel is the edge of the universe and the movie is reality itself. When particles collided in the early cosmos, forming the first bonds, their interactions might have been shadows of deeper 2D processes, like echoes of a hidden code. This bizarre connection isn't just speculation, it stems from black hole physics. When scientists calculated how much information a black hole can hold, they found its entropy, its chaos, doesn't scale with volume but with surface area. That revelation sent shockwaves through physics. What if everything follows this rule? Here's where chemistry comes in. If early molecular bonds were projections of 2D data, it could explain certain puzzles, like why quantum particles seem to know how to react instantaneously across vast distances, or why some elements appear evenly distributed in ways classical physics struggles to justify. A few daring theorists even suggest this holographic layer might have acted like a cosmic recipe book, pre-configuring reactions before they unfolded in 3D space. Of course, not everyone's convinced. Critics argue we lack direct evidence that holography shaped early chemistry. It's still largely mathematical elegance. But supporters point to recent quantum simulations where lower-dimensional systems mimic higher-dimensional chemistry with eerie accuracy. Whether this principle truly governed the universe's first bonds remains an open question, one that could redefine not just chemistry's origins, but the very nature of reality itself. And if future experiments find traces of this holographic code etched into the cosmos, it would mean every atom in your body, every star in the sky, is part of the most elaborate projection imaginable, a universe painting its own chemistry onto the canvas of space-time. Deep in the heart of the early universe, before electromagnetism took hold, there may have been a hidden player in chemistry's origin story: axions. These ghostly hypothetical particles, originally proposed to solve a puzzle in quantum physics, could have been the universe's first matchmakers, nudging atoms together when no other force was strong enough to do the job. Picture this: a cosmos so young that light as we know it couldn't yet travel freely, where charged particles swam in a thick plasma. Normally, atoms need electromagnetic forces to bond, but axions might have offered a temporary workaround, acting like cosmic glue before the rules of chemistry were fully written. What makes axions so intriguing isn't just their potential role in bonding, it's their dual identity as leading dark matter candidates. If they exist, these particles would barely interact with normal matter, slipping through the universe like whispers. Yet in those extreme early conditions, even subtle interactions might have left fingerprints on the first chemical reactions. Some models suggest axions could have mediated brief handshakes between particles, creating fleeting bonds that dissolved once electromagnetism took over. It's as if the universe used a shadow chemistry before discovering the real thing. The hunt for axions is heating up in labs worldwide. Underground detectors and powerful magnetic experiments are searching for the faintest traces of these elusive particles. If found, they wouldn't just solve a dark matter mystery, they could rewrite our understanding of how the first molecular connections formed. Imagine confirming that the same invisible particles shaping galaxies today also helped spark chemistry at the dawn of time. Until then, axions remain one of physics' most tantalizing what-ifs, a reminder that the universe's first reactions might have been guided by forces we're only beginning to dream of. Now consider this: what if space-time itself isn't smooth like a sheet of glass, but more like a finely woven fabric, one made of unimaginably tiny loops? That's the radical idea behind loop quantum gravity, a theory suggesting that on the smallest scales, the fabric of reality is stitched together by discrete, interwoven threads. And if this is true, it might mean the universe's first chemical reactions didn't just play out on the stage of space-time, they were shaped by its very texture. In classical physics, reactions happen against the backdrop of a continuous, unbroken universe. But loop quantum gravity paints a different picture, one where spacetime's granularity could have acted like microscopic speed bumps or tunnels, subtly altering how particles moved and collided. Imagine trying to dance on a floor made of trampolines versus one made of gravel. The uneven terrain changes everything: your steps, your rhythm, even how easily you can reach your partner. In the early cosmos, these quantum loops might have done something similar, creating pockets where reactions accelerated or slowed in ways no textbook could predict. The numbers are staggering. Some calculations suggest that at temperatures approaching 10 to the 32 degrees, conditions so extreme they make supernova look tame. These space-time loops could have compressed particles together with enough force to bypass normal reaction barriers. Think of it like threading a needle where the needle itself helps guide the thread. For brief moments, hydrogen nuclei might have fused not because of heat or pressure, but because spacetime's graininess nudged them into alignment. Yet here's where things get contentious. Critics argue that while loop quantum gravity is mathematically elegant, its effects on chemistry would have been vanishingly small, like trying to hear a whisper in a hurricane. But supporters counter with models showing how these subtle shifts could have snowballed over time, leaving fingerprints in the uneven distribution of elements we see today. Whether these quantum loops truly shaped chemistry's dawn remains one of theoretical physics' most thrilling debates. One thing's certain: if future experiments ever confirm spacetime's granular structure, we might be looking at the universe's first reactions in a radical new light, not as events in space and time, but as dances choreographed by the very fabric of reality. Now let's dive into one of physics' great what-ifs: magnetic monopoles. These hypothetical particles, carrying just a single magnetic charge, were first dreamed up by Paul Dirac in the 1930s. While we've never found one, their fingerprints might be hidden in the universe's earliest chemical reactions. Picture the cosmic plasma not as a formless soup, but as a seething electric storm, charged particles swirling in chaos. Monopoles could have been the missing organizer's tiny cosmic magnets cutting through the turbulence, aligning currents like invisible conductors guiding an orchestra. Here's how it might have worked. As monopoles zipped through the early plasma, their powerful magnetic fields could have funneled ions into dense filaments, creating pockets where collisions, and thus chemical reactions happened far more frequently. Think of it like stirring cream into coffee. Without the spoon, the mixing takes ages, but drop in just one monopole and suddenly, particles find each other faster, bonding in ways nature's randomness wouldn't allow. Some theories suggest this could have accelerated the formation of the first hydrogen molecules, jump-starting chemistry before stars even ignited. But if monopoles were so crucial, where are they now? That's the puzzle. Inflation, the universe's explosive early expansion, might have diluted them to near non-existence, leaving just a handful scattered across billions of light years. Or perhaps they're hiding in plain sight, masquerading as dark matter or lurking in cosmic rays. The hunt isn't over. Experiments like Mo-Edel at CERN are chasing even the faintest magnetic anomalies, while astrophysicists scan ancient starlight for monopole shadows. What's tantalizing is this: if monopoles did shape the first reactions, they'd leave a signature in how matter clumped together. Modern telescopes mapping the cosmic web might already hold clues, unexplained voids or filaments that align a little too perfectly, as if traced by an unseen magnetic hand. Whether relic or ghost, these phantom particles remind us that the universe's first chemistry might have been orchestrated by forces we're only beginning to imagine, and that some of its greatest architects could still be waiting in the dark. Among the most mysterious forces shaping our cosmos, dark energy reigns supreme, an unseen driver pushing galaxies apart faster and faster. But what if this phantom force wasn't just a late game player? Some theorists propose dark energy might have been active from the very beginning, subtly warping the pathways of the universe's first chemical reactions. Imagine the early cosmos as a bubbling cauldron of particles, where even the slightest nudge could alter how atoms connected. Dark energy, if present in those initial moments, would have acted like an invisible hand gently bending the rules. Normally, particles bond based on well-understood forces, but with dark energy in the mix, reaction pathways might have twisted unpredictably. Picture trying to navigate a maze where the walls themselves shift as you move, some bonds forming easier, others suddenly out of reach. This isn't just wild speculation. Observations of today's accelerating expansion hint that dark energy's influence evolves over time. If it was stronger in the past, even by a tiny fraction, it could have left subtle traces in the distribution of hydrogen and helium. Some models suggest regions where dark energy's push was slightly stronger may have hosted unusual molecular formations like cosmic eddies in an otherwise smooth flow. Yet the puzzle deepens. If dark energy played a role in early chemistry, why hasn't its fingerprint been spotted yet? The answer might lie in the delicate balance of forces. Even a minuscule interaction could have snowballed over billions of years, leaving patterns too faint for current telescopes to detect. Future missions, like the European Space Agency's Euclid telescope, aim to map dark energy's influence with unprecedented precision, potentially uncovering echoes of its early meddling. Whether dark energy shaped the first atomic handshakes or merely watched from the shadows remains one of cosmology's great open questions. But one thing's certain: if this phantom force truly tweaked the universe's first reactions, it would mean chemistry's rulebook wasn't just written by familiar physics, but by something far stranger, hiding in the empty spaces between stars. At the very edge of physics, where matter gets squeezed beyond imagination, lies a clue to the universe's first chemical secrets: neutron stars. These stellar corpses pack more mass than our sun into a sphere barely the size of a city, creating crushing densities where a single teaspoon of material would weigh billions of tons. But here's the astonishing part: the bizarre nuclear reactions happening on their surfaces today might mirror what unfolded everywhere moments after the Big Bang. Picture the surface of a neutron star, an expanse where gravity is so intense it strips atoms down to their bare skeletons. Electrons get smashed into protons, forming neutrons, while residual nuclei get stretched into bizarre, spaghetti-like shapes physicists call nuclear pasta. This isn't just a cosmic oddity, it's a snapshot of high-pressure chemistry pushed to extremes. Under these conditions, particles bond in ways that defy earthly physics, forming clusters so dense they blur the line between nucleus and molecule. Now rewind to the early universe. For a fleeting period, the entire cosmos was under pressures rivaling a neutron star's crust, a time when matter was squeezed so tightly that normal atomic bonds couldn't exist. Instead, exotic nuclear molecules might have flickered into being, unstable alliances forged in the fire of creation itself. Some researchers propose these ephemeral structures acted like cosmic scaffolding, guiding how later, more stable elements formed. It's as if nature was running trial versions of chemistry before settling on the rules we know today. The echoes of this era might still be detectable. When neutron stars collide, an event so violent it shakes spacetime, they spew out material enriched by these extreme reactions. Spectra from these crashes show traces of heavy elements like gold and platinum, hinting that similar high-pressure synthesis could have happened in the infant universe. If so, the same exotic bonds that glitter in neutron star debris might have once been the universe's first chemical handshakes. Of course, not all scientists are convinced. Critics argue the early universe's conditions, while extreme, differed too much from neutron stars for direct parallels. Yet supporters counter with supercomputer simulations showing how nuclear pasta-like phases could have emerged fleetingly before dissolving into the cooling cosmos. Whether neutron stars are perfect analogues or just cosmic cousins, One thing's clear: studying these extreme laboratories gives us a glimpse into a time when chemistry wasn't just new but utterly alien. And buried in their crushing embrace might lie answers to how the first atomic dances began. Picture this: parallel universes aren't just distant realms beyond our reach, but bubbles bumping into one another like soap suds in a cosmic sink. When these bubbles collide, they don't just pop silently. They leave behind radioactive scars, traces of chemistry that shouldn't exist in our universe. This is vacuum decay residue, the aftermath of a multiverse fender bender where the laws of physics themselves got reshuffled. At the heart of this wild idea is something called the false vacuum, an unstable state where the universe's fundamental forces could be teetering on the edge of collapse. Think of it like standing on a frozen lake that might crack beneath you at any second. If another universe's bubble brushed against ours, it might have left behind pockets where particles behave differently, where hydrogen bonds warp or electrons move just a fraction slower. These anomalies wouldn't just be quirks, they'd be breadcrumbs leading back to collisions with other realities. Here's where it gets speculative and thrilling. Some cosmologists suggest these residues could have acted like cosmic catalysts, jump-starting reactions in the early universe that otherwise would have needed stars or black holes. Imagine finding a lighter in a world that hasn't discovered fire. That's the kind of shortcut we're talking about: exotic chemistry imported from a universe with totally different rules. But there's a darker twist. If vacuum decay residues are real, they might not just be relics, they could be ticking time bombs. Theoretical models show how these zones of altered physics could destabilize surrounding matter, triggering chain reactions that rewrite local laws of nature. It's as if the universe's code had a few corrupted lines, and no one knows when they might crash the system. Of course, not everyone buys into the drama. Skeptics argue that even if bubble collisions happened, their residues would have diluted to nothing over billions of years. But supporters point to oddities in deep space spectroscopy, regions where elemental ratios defy expectations, or where energy signatures flicker like glitches in reality's matrix. Until we have better data, vacuum decay remains one of cosmology's most tantalizing what-ifs, a reminder that our universe's first chemistry might have been shaped by crashes with worlds we'll never see. And if that's true, every atom in your body could carry echoes of a multiverse you never knew existed. Now let's turn to something invisible yet powerful enough to stir the entire cosmos: gravitational waves. These ripples in space-time, first predicted by Einstein, aren't just cosmic curiosities. They might have been the universe's first mixers, violently shaking matter into reactions that shaped everything we know. In the early universe, gravitational waves weren't the faint whispers we detect today. They were tsunamis, colossal distortions born from the Big Bang's shockwaves and the violent mergers of infant black holes. Picture a pot of water set to boil. The bubbles don't just rise gently, they churn, collide, and burst with energy. Now imagine that same chaos, but scaled up to cosmic proportions, with gravitational waves sloshing through the primordial plasma like an invisible spoon. Under that turbulence, particles wouldn't just drift, they'd be hurled together with extreme force, overcoming the natural barriers that usually keep them apart. Hydrogen and helium nuclei, which might have taken eons to bond under calm conditions, could have been smashed into fusion in mere moments, forging the universe's first heavy elements long before stars lit up. Some simulations even suggest these waves created dense pockets where chemistry unfolded at hyperspeed, like cosmic accelerators hidden in the fabric of spacetime itself. The wild part: we might already have clues. When LIGO detected gravitational waves in 2015, it proved these ripples carry energy across billions of years. While today's waves are too weak to influence chemistry, their ancient ancestors could have packed enough punch to kickstart reactions. Future detectors, like the proposed Einstein telescope, might uncover traces of these primordial Goliaths in the cosmic microwave background, subtle swirls left behind by waves that once stirred the universe's first atomic soups. Not all scientists are convinced, of course. Critics argue that gravitational waves, while powerful, would have needed impossibly precise frequencies to trigger specific reactions. But supporters counter with models showing how chaotic resonance could have amplified their effects, turning random jostling into a finely tuned molecular dance. Whether proven or not, this idea forces us to rethink chemistry's origins not as a quiet process, but as a storm where space-time itself was the chef, whisking the universe's first ingredients into existence. Now let's stretch our imaginations literally into the hidden dimensions that might have shaped the universe's first chemistry. In the 1920s, physicist Theodore Kaluza proposed a radical idea. What if our universe isn't just three-dimensional, but curled up with tiny, unseen extra dimensions? Later refined by Oscar Klein, this Kaluza-Klein theory suggests particles vibrating in these higher dimensions could have acted as invisible matchmakers, mediating reactions between ordinary matter in ways we're only beginning to grasp. Think of it like this: if our familiar three dimensions are the strings on a guitar, these extra dimensions would be harmonics, vibrations too subtle to hear but influencing the overall sound. In the early universe, Kaluza-Klein particles might have carried forces that bypassed normal physics, allowing atoms to bond across barriers that should have been impossible. Hydrogen nuclei separated by vast distances could have felt each other through these hidden channels, snapping together like magnets guided by an unseen hand. But here's the catch: for this to work, those extra dimensions had to be compactified, curled up so tightly that even atoms couldn't perceive them. Picture a garden hose. From a distance, it looks like a simple line, but up close, you see it's actually a cylinder. Similarly, these dimensions might have been folded into intricate shapes at scales a billion times smaller than an atom, the challenge proving they existed at all. Without direct evidence, Kaluza-Klein particles remain ghostly suspects in chemistry's origin story, powerful in theory, elusive in practice. Recent string theory models offer tantalizing hints, though. If these higher dimensional vibrations left imprints on the cosmic microwave background, future telescopes might spot their fingerprints as faint temperature anomalies. Others propose that high-energy particle collisions could temporarily uncurl compactified dimensions, creating signatures detectable in labs like CERN. Until then, this idea remains a beautiful what-if, a reminder that the universe's first chemical handshakes might have been guided by forces we can't even see, humming silently in the spaces between dimensions. Here's something that bends the mind: what if the universe's first chemical reactions didn't just depend on particles bumping into each other, but on ghostly quantum links that spanned the entire cosmos? This is the wild idea behind entanglement-driven chemistry, the notion that particles could coordinate reactions instantly across vast distances, as if the universe itself was whispering instructions between them. Picture two electrons born together in the early universe's chaos. Thanks to quantum entanglement, no matter how far apart they drift, changing one instantly affects the other, like cosmic twins sharing a single heartbeat. Normally, we think of chemistry as a local affair. Atoms need to be close enough to touch, or at least feel each other's electromagnetic pull, but entanglement flips that script. Experiments here on Earth have shown entangled molecules reacting in eerie sync, even when separated by distances that should make coordination impossible. It's as if the molecules know what the other will do before it happens. Now scale that up to the infant cosmos, a place so dense that particles were constantly entangling and disentangling in a frenzied quantum dance. Under those conditions, reactions might have unfolded like a perfectly timed orchestra, with particles light years apart somehow choosing to bond in harmony. Some theorists argue this could explain how certain elements spread so uniformly across the universe, like a hidden quantum hand guiding the distribution. Of course, not everyone's convinced. Skeptics point out that entanglement is notoriously fragile. Even a single stray photon can sever the connection. But supporters counter with lab breakthroughs where entangled molecules maintain their eerie coordination long enough to complete reactions, defying classical expectations. If similar resilience existed in the early universe's extreme environment, it could mean chemistry's rulebook was written not just by forces we understand, but by quantum weirdness we're only beginning to unravel. The implications are staggering. If entanglement truly steered the first chemical bonds, it would mean the universe's blueprint for matter wasn't just local, it was everywhere at once. And buried in the quantum links between atoms today might be echoes of that ancient invisible network, still humming beneath the surface of reality. Now let's flip the script on black holes entirely, because if Einstein's equations hold true, there might be cosmic counterparts lurking in the early universe's shadows, white holes. These hypothetical twins would operate like black holes in reverse, violently spitting out matter instead of trapping it forever. And here's the twist: that ejected material might have been the universe's first pre-packaged chemistry kits, pre-forged in conditions we can barely imagine. While black holes crush matter into oblivion, theoretical white holes could have done the opposite, spewing out clusters of atoms already processed under extreme pressures and temperatures. Think of it like a cosmic conveyor belt. Matter gets pulled into a black hole, stretched and scrambled beyond recognition, then potentially reborn through a white hole with its properties utterly transformed. Some models suggest these ejecta could have contained exotic molecular arrangements or even heavy elements, skipping the slow fusion processes of stars entirely. The thermodynamics here are mind-bending. Black holes obey strict entropy rules. They're the ultimate cosmic shredders. But white holes, they'd be more like fireworks bursting with energy and complexity. If they existed in the early universe, their outbursts could have seeded regions with unusual chemistry, like pockets of pre-assembled matter ready to jumpstart reactions wherever they landed. Not everyone's sold on the idea, of course. Critics point out that white holes violate our current understanding of causality. They're mathematical curiosities with no observed counterparts. Yet supporters counter with intriguing possibilities. Certain gamma-ray bursts or unexplained elemental abundances in deep space could be fossil traces of these cosmic fountains. Whether real or just a beautiful thought experiment, white holes challenge us to reconsider where and how the universe's first chemical ingredients might have been cooked up. After all, if chemistry's rulebook was written in the fire of the Big Bang, maybe some of its pages were drafted in places where time itself flows backward. Deep in the universe's fiery infancy, there may have been a boiling point so extreme it forced matter itself to reboot. Physicists call it the Hage-Dawn temperature, a theoretical threshold where particles stop behaving like individual entities and melt into a seething, indistinguishable soup. Picture trying to cook with water that suddenly refuses to boil hotter, no matter how much heat you add. At this critical point, the normal rules of chemistry would have shattered entirely, forcing reactions to start from scratch under entirely new conditions. This wasn't just about extreme heat, it was a total phase shift, like flipping a cosmic switch. Normally, as temperatures rise, particles move faster and collisions grow more violent. But reach the Hage-Dawn limit and something bizarre happens. Instead of breaking apart further, matter hits a wall, as if the universe had maxed out its thermometer. At this point, protons, neutrons, and other particles would have dissolved into a plasma of their building blocks, quarks and gluons unshackled from their usual bonds. Here's the game changer for chemistry's origins. As the universe cooled back below this threshold, those freed quarks and gluons didn't just snap back into their old arrangements. They recombined in unpredictable ways, potentially forging exotic short-lived particles that acted like molecular trial runs. Some theories suggest this chaotic reshuffling could have seeded the first stable hydrogen and helium nuclei, letting chemistry proper begin only after this great cosmic reset. Evidence for this theory hides in the debris of particle colliders. When scientists smash heavy ions together at near light speed, they recreate fleeting moments of quark-gluon plasma briefly touching temperatures that might mirror the Hagedorn limit. The resulting particle showers show strange distributions, hints of matter caught mid-transformation. If similar patterns exist in the cosmic microwave background's faint imprints, we could be looking at fossils from the moment the universe's chemistry hit pause and rebooted into the cosmos we know. Skeptics argue the Hagedorn temperature might have been too fleeting to leave lasting marks, but supporters counter that even a split-second reset could have skewed how elements formed, like a baker briefly cranking the oven to its maximum before settling on the perfect temperature. Whether proven or not, this idea forces us to wonder, did chemistry's rulebook have a rough draft, one that got erased when the universe itself overheated? At the cutting edge of theoretical physics lies a phenomenon that might have twisted the first chemical reactions into existence: Chern-Simons vortices. These swirling knots in the quantum fabric of space-time aren't just mathematical curiosities. They could have been the universe's earliest molecular workshops. Imagine a cosmic whirlpool, but instead of water, it's spinning threads of pure force twisting particles together with a grip so precise it defies classical physics. In the seething plasma of the infant cosmos, these vortices wouldn't have behaved like ordinary matter. Governed by topological quantum field theory, a framework that treats particles like braids in space-time, they might have corralled chaotic particles into ordered collisions. Picture a tornado funneling scattered leaves into a tight spiral, except here, the leaves are hydrogen nuclei forced into proximity just long enough to bond. Condensed matter experiments on Earth offer eerie parallels when physicists create artificial systems mimicking Chern-Simons effects. Particles inside them start behaving like synchronized dancers, reacting in lockstep despite no obvious force connecting them. What chills spines is the math behind this. Chern-Simons theory predicts these vortices would have left ghostly imprints on quantum fields, subtly steering reaction pathways like invisible rails. Some models suggest they could have even skewed the odds, making certain molecular formations statistically inevitable where randomness should have ruled. If true, it means the universe's first chemistry wasn't just accidents in a chaotic soup. It was choreographed by spacetime's hidden geometry, yet skeptics aren't sold. Without direct evidence from the early universe, Chern-Simons vortices remain breathtaking hypotheses, but supporters point to modern quantum materials, like graphene under extreme conditions, where analogous vortex effects emerge, hinting that nature might reuse its most elegant blueprints across scales. Whether these quantum whirlpools truly shaped cosmic chemistry or not, they remind us that the rules of bonding might be written not just in particles, but in the very twists and knots of reality's fabric. Now let's plunge into one of the universe's most extreme makeovers: neutronization. This bizarre process didn't just tweak atoms, it stripped them down to their bones, transforming familiar protons into neutrons under pressures so intense, even atomic nuclei couldn't hold their shape. Picture the early cosmos as a cosmic smelting furnace, not just melting matter, but fundamentally rewriting its blueprint. In the crushing depths of primordial plasma, where gravity squeezed matter beyond recognition, protons drowned in seas of electrons. The force was so overwhelming that protons and electrons fused, morphing into neutrons and neutrinos in a flash. These weren't gentle reactions, they were particle alchemy at its most violent. What emerged were neutron-rich molecules, exotic clusters that scoffed at normal chemistry's rules. Today, we catch glimpses of this process in neutron stars, where matter is so compressed it's essentially a giant atomic nucleus. But in the universe's infancy, entire regions might have undergone similar transformations. forging neutron-rich isotopes that shouldn't exist under ordinary conditions. Some theorists suggest these ephemeral molecules acted as cosmic stepping stones, bridging simple elements to the complex ones that would later seed stars and planets. Yet mysteries linger. If neutronization was so widespread, why didn't it lock the universe into a neutron-dominated dead end? The answer might lie in balance, just enough conversions to diversify matter, but not so many that protons vanished entirely. It's a razor's edge between creation and stagnation, one that shaped the chemistry we take for granted. And buried in ancient stardust, we might yet find traces of these ghostly neutron-rich relics, the universe's first experiments in extreme atomic architecture. Now let's step into one of the most mind-bending ideas in all of physics, a universe born not from a single explosive moment, but from the shattering collision of entire dimensions. This is brain cosmology, a vision where our Big Bang might have been just one violent encounter in an endless cosmic cycle. Picture two massive, parallel universes floating like sheets of paper in some higher dimensional space, suddenly slamming together with unimaginable force. The energy released wouldn't just create stars or galaxies. It could have forged the very first chemical bonds in the fire of that impact. In string theory, these vast dimensions are called branes, short for membranes, and when they collide, the results are anything but quiet. The shockwaves would have blasted particles into existence, scattering them like cosmic shrapnel. But here's the twist: some models suggest these collisions wouldn't just leave behind random debris. The way branes stretch and warp during impact could have imprinted patterns on matter itself, like ripples in a pond freezing into ice. Certain elements or molecules might have formed more readily in the aftermath, as if the physics of the collision pre-wired chemistry's first reactions. This isn't just about one Big Bang either. Cyclic universe models propose that these brain collisions happen over and over, an endless cycle of creation, expansion, and collision. In this view, the hydrogen in your body might have been forged not just once but countless times, recycled through cosmic crashes we can scarcely comprehend. It's a dizzying thought. Every atom in existence could be the remnant of a collision between realities we'll never see. Yet the most tantalizing clue might be hidden in the cosmic microwave background. If brain collisions leave behind subtle temperature variations like wrinkles in spacetime's fabric, future telescopes might spot their fingerprints. Until then, this theory remains a breathtaking what if, challenging us to rethink not just how chemistry began, but whether our universe is alone, or just one page in a much, much stranger book. What if the universe's first chemical reactions weren't just random collisions, but the output of an ancient cosmic computer? That's the radical idea behind information-theoretic chemistry, where atomic bonds form not by chance, but as deliberate computations in the fabric of reality itself. Picture this: every particle interaction as a line of code in a vast quantum program, with energy not just fueling reactions but paying the processing cost. This ties into Landauer's principle, a fundamental rule stating that erasing information always requires energy. In the early universe, that energy currency might have dictated which reactions succeeded and which fizzled out. Think of it like a cosmic app store. Only the most efficient molecular algorithms got to run, while energy-intensive ones crashed before they could execute. Here's where it gets surreal. Some theorists suggest quantum entanglement could have acted like a network, linking particles across space so they computed bonds in unison without physical contact. Imagine two hydrogen atoms forming a molecule not because they bumped into each other, but because their quantum states resolved an equation like distant servers syncing data. Critics argue this blurs the line between metaphor and mechanism. Can chemistry truly be reduced to information? Yet lab experiments with quantum computers show molecules forming in ways that mirror computational optimizations, as if nature itself prefers elegant code. If the universe really did run its first chemistry as a quantum program, It would mean every atom around us carries echoes of the cosmos' original programming language, a thought that redefines not just our past but the very nature of reality. Now let's explore a theory where gravity itself might have been fashionably late to the cosmic party: emergent gravity. This radical idea flips everything we thought we knew. Instead of gravity being one of the universe's fundamental forces from the start, what if it only showed up after the first chemical reactions were already underway? Picture the early cosmos as a stage where electromagnetism and nuclear forces were the main actors, bonding atoms with no gravitational interference until suddenly, the backdrop shifts and gravity steps into the spotlight, rewriting the rules of chemistry mid-scene. At the heart of this theory is physicist Eric Verland's entropic gravity, a concept that reimagines gravity not as an innate force, but as an effect emerging from the way information scrambles across the fabric of spacetime. Think of it like the way temperature isn't a thing in itself, but a measurement of how fast particles are jiggling. In this view, gravity could have been a latecomer, only kicking in once the universe cooled enough for entropy, the universe's built-in chaos meter, to start playing a role in how matter organized itself. Here's why that matters for chemistry's origins. Without gravity's pull in those earliest moments, particles might have bonded in ways that seem impossible today. Hydrogen and helium nuclei could have formed loose, fractal-like structures, unburdened by the crushing weight that later shaped stars and galaxies. Then, as gravity switched on, those delicate arrangements would have collapsed into denser clusters, triggering a second wave of reactions. It's like building a house of cards in zero gravity, only for someone to suddenly flip on Earth's pull. What was once stable would instantly reconfigure. The echoes of this transition might still be visible. Some astrophysicists argue that certain anomalies in the cosmic microwave background, the afterglow of the Big Bang, could hint at regions where gravity's emergence left scars. Others point to the puzzling distribution of dwarf galaxies, which clump together in ways that don't quite match predictions from standard gravity models. Could these be fossils of a time when chemistry played by different rules before gravity took its seat at the table? Of course, not everyone's convinced. Critics contend that if gravity emerged late, we'd see far more dramatic inconsistencies in the universe's structure. Yet simulations incorporating emergent gravity show tantalizing possibilities, like a cosmic before and after snapshot, where the first molecular bonds were forged in gravity's absence, only to be reshaped when it finally arrived. Whether this theory holds up or not, it forces us to rethink a fundamental truth: the laws we take for granted today might not have always been in charge. And if gravity truly was a late bloomer, the universe's first chemistry might have been wilder, freer, and far stranger than anything we've ever imagined. Now we arrive at one of the most unsettling ideas in cosmology, the Boltzmann brain paradox. What if the universe's first chemical reactions weren't just random events, but fleeting hallucinations of a consciousness that blinked into existence for a fraction of a second? Picture a self-aware bubble of atoms, convinced it's witnessing the birth of chemistry, only to dissolve back into the void before reality can even correct it. The paradox gets its name from physicist Ludwig Boltzmann, who grappled with how order emerges from chaos. In an infinite universe, he reasoned, even the most improbable things must happen, including isolated brains materializing from random particle collisions. Stretch that idea to the extreme, and you get a wild possibility. Some of the earliest molecular bonds might have been observed by these phantom minds, their brief flicker of awareness mistaking cosmic noise for structure. Here's where it gets weirdly plausible. Quantum mechanics allows for particles to arrange themselves in seemingly impossible configurations, just not for long. A Boltzmann brain wouldn't need to last, it just needs to think it lasted long enough to perceive something coherent. So when we analyze ancient chemical signatures today, could we be studying the remnants of a cosmic dream? Critics pounce on this theory's unfalsifiability. It's impossible to disprove because any evidence against it could just be part of the hallucination. But supporters counter with a haunting question. If consciousness can emerge from atoms, why wouldn't it have happened amid the chaos of the early universe? It's a dizzying loop, like finding a note you wrote to yourself only to realize the handwriting isn't yours. Whether you dismiss it as philosophical mischief or entertain it as a radical possibility, the Boltzmann brain forces us to confront an eerie truth. Our entire cosmic history might rest on perceptions no more lasting than a spark in the dark. And if that's the case, the universe's first chemistry wasn't just about atoms bonding. It was about reality itself struggling to decide what was real. From quantum whirlpools knitting atoms together to collisions between entire dimensions, we've journeyed through some of the most daring ideas about how chemistry first sparked to life in our universe. Think about it: black holes as cosmic alchemists, ghostly neutrinos nudging particles into place, or even reality itself running chemistry like a quantum computer program. These aren't just wild guesses, they're testaments to human curiosity, each one stretching the limits of physics as we know it. Some theories feel almost within reach, like primordial black holes hiding in plain sight, while others, like entanglement weaving molecules across light years, challenge everything we thought possible. And that's the beauty of cosmology. Even the most outlandish ideas push science forward, forcing us to ask better questions. Maybe dark energy seasoned the cosmic soup, or neutron stars left behind exotic molecular blueprints. Perhaps chemistry's rules were rewritten when gravity finally woke up to the party. Here's where you come in. Which theory sparks your imagination the most? Drop your favorite in the comments. Debate whether vacuum decay, residue, or supersymmetry deserves the spotlight. Because unraveling these mysteries isn't just about the past, it's about the puzzles still waiting to be solved. And trust me, the universe has plenty more secrets up its sleeve. From the holographic echoes of hidden dimensions to the lingering whispers of white holes, our next cosmic deep dive might just rewrite the story all over again. Until then, keep looking up and never stop wondering what else is